So what we're going to do today is scalable geospatial computing. So week 10 is up here, and I'm going to go through these notebooks, and then Dylan's going to take over doing a lot more stuff. Okay, so what is geospatial analytics? And what is scalable geospatial analytics? Right, so let's listen to this. This is just from the Spark Summit East, very, very recent.
So basically the problem that they're trying to solve is geospatial analytics, right? And geospatial analytics is any type of analytics that uses spatial structure and spatial context for processing, right? So I've picked 3 use cases here. These are just 3 examples. There's tons and tons of use cases that people encounter. And after the talk, I'd be happy to discuss more use cases, or if you can come up with a new use case, that's even more awesome. But let's say, take an example as Uber, right? So Uber collects mobile data about passengers, about trips, and so on. And if you're Uber, you're likely interested in things like, how does the pickup and drop-off neighborhood hotspots change with time, right? So sometimes it's Soma that's the hotspot for pickups and drop-offs in San Francisco. Sometimes it's actually a different region, different neighborhood in San Francisco, and this changes with time. So a problem like this is basically a spatial temporal analytics problem. Right? And this is an example of a business intelligence query that uses geospatial context. So the context that uses here is basically mobile data. Somebody has to figure out, given latitude and longitude, what neighborhood of San Francisco or what neighborhood of New York is it, and then use it in an aggregate query or something. Second problem is, this is fairly canonical for railroad companies or transportation companies and so on. So you collect GPS data, so mobile data is basically GPS coordinates, and GPS coordinates have a certain accuracy limitation on them. But let's say that you are a railroad company and you actually have very, very fine measurements about the railroad tracks. What I've shown here is a very smooth curve. Obviously, the real world data is not that smooth. But let's say you have data about the railroad tracks at the feet level, then can you actually correct the GPS errors? So the idea here is, can you correct GPS errors with more accurate landmark measurements? Now, obviously, to do this, you have to understand what is actually going along this path. If it's a train going at a uniform velocity, it's easier to correct that. If that's not the case, it's a more complex problem. But in either case, problems like this involve looking at points, snapping them to the closest grid, and figuring out what the point is that lies on the grid that's closest to this point is. So it's like an example of a near neighbor query.
So this is called map matching, and hopefully Dylan will have time to get into map matching. This is also the problem that Khalid has with agricultural robots and fruit orchards in Canterbury. So your maps will be the pathways the robots could take, and then you have some GPS signals, and once again, noise is there. So you have to do some map matching to map the actual location to the paths they're assigned to transport fruits on or whatever.
The third piece of it, which is kind of the original problem that I started looking at for geospatial context, is search error data, right? So I have an example here where somebody types in canyon on Google search, and you notice that there's a few things that pop up. Now, there is some ranking algorithm that goes and figures out, what do you mean here? Do you really mean the Canyon Hotel, for example, or do you mean Grand Canyon, or do you mean Canyon Ranch, and so on? Now, actually, I did this query in Google yesterday, and I was in New York at this time. Now, Canyon Road, New York City shows up as a kind of 4th option here. And Canyon Ranch is actually in Texas. So, I was really not looking for Canyon Ranch, right? So somehow your search engine should do a better job of knowing where you are and figuring out what query is actually where.
Okay, so that sort of gives you an idea, right? So you can use geospatial analytics in lots of contexts. And most of the emphasis there was on the last example anyway, was on business analytics, because Ram Sriharsha, this guy that's behind Magellan, worked in Yahoo and geospatial research and some other stuff. So here are some concrete examples of scalable geospatial analytics for us to consider. So this is hopefully where some of you can take the various bits and bobs we've learned throughout the course. Basically, this is the last lecture, right? And put it all together, right? One way you can put it all together, this is like the tweet data, for example. We did a lot with Twitter streams and turn them into graph objects, and we can do a lot more with logistic and linear regression from sensors. And so how do you sort of combine a lot of this data to get knowledge? This is, Microsoft Research has this urban computing group. It's based in Beijing. So in fact, the data set Dylan will talk about is the Beijing taxi trajectory data, which is a well-known data set in spatial trajectory computing. So what's urban computing? Basically, it's the process of acquisition, integration, analysis of big and heterogeneous data sources from completely different sources, right? From a heterogeneous set of sources. It could be trajectories of vehicles, it could be cell phone information, social media information, all sorts of things, you know, if you even have credit card transaction and more, whatever else you want. Okay, so there's a lot of papers about this. So there's papers almost every year. It's a very active field. There is a Geospatial Research Institute or Research Center at UC. Unfortunately, nobody here is from the center. They have a lot of plans to do things like this, urban computing and forestry sensing and things like this. So a lot of these technologies allow you to take input streams from a lot of heterogeneous sources and then somehow combine them in a very nice, scalable, intelligent environment, where you can use like Spark SQL and machine learning library and all of this in one cohesive place. Okay. So this is just different examples here. Some predicting fine-grained air quality. I looked at this paper at one point in Beijing. They want to, you know, there's sensors measuring CO2 concentrations and so on and so forth. Okay.
You know that there was similar for
This
Christchurch.
is a good one as well. I don't know. I'm not sure.
Sensing City.
Yeah, but I'm not sure how far the whole sensing cities go. We have to first build the city, right? I mean, yeah, I know that one of the buildings has the sensors, the Trimble building, right? It has all the sensors all over the building to measure earthquakes and stuff. But
They had big plans, but they cut it.
they cut it. Yeah, okay, yeah. Guadalajara, Mexico, I think really beat us. That was in IEEE transactions as one of the model cities for these kinds of things. So this is urban denoising. So Manhattan is part of the open data cities, I think. Chicago as well. So lots of cities in the US are joining this open data movement. So they're sort of streaming lots of data, like their 311 telephone calls on complaints. You can just plug in, listen to it. Crimes, for example, all sorts of things, okay? So this is some city noise maps and ride sharing, travel time estimation. So a lot of these things involve spatiotemporal data, and so you can knock yourself out on a lot of these papers. So Dylan's thing is talking specifically about a paper here. I think he's linked to it. Yeah, this is again quite interesting, the urban anomaly detection problems. So you're trying to detect collective anomalies by fusing information across multiple domains. This is a very beautiful paper, actually. So what do? They have bike sharing data in Manhattan. So people like taking bikes from one stand, putting it in another stand. And then they have taxi trajectory data. And then they had 311 telephone call complaints data and some kind of social media natural language processing layer on top of it. So, you know, if people are complaining about, getting congested or whatever, and there are 311 calls coming from a region, they want to basically use all these different signals to detect anomalies so they can maybe anticipate congestions, right? So it's a really interesting paper. I think some of the intuitions they have could be better understood with some more classical statistical methods. Okay, so I'm not going to go through all of this. Knock yourself out. There's a lot in urban computing world. That's just one field, right? They have their own conferences and stuff. Of course, several sciences, natural sciences are in this space as well. Forestry, geography, geology, seismology, and so on and so forth. Agricultural robotics, for example. Okay. So this is just some US Geological Survey actually provides real-time data of earthquakes. I think they guaranteed 30 minutes after an event outside California and I think a few minutes right after an event in California, you can get all this data. So now, this is kind of a crazy idea, but imagine the non-parametric inference problem of estimating, you can think of these as sort of co-exciting Hawkes processes, for those who know what it is, on the entire planet. So you basically have events happening on the entire surface. And there are sensors, in the ocean beds and everything, right? So you have incredible coverage of earthquakes. So now, can you actually make models that are, completely global, right? The arithmetic capabilities and the scalable, arithmetic capabilities you need to do that estimation, I believe, is basically what Magellan gives you a helping hand with, and Magellan is actually growing quite fast. So, okay, so hopefully these kinds of problems can be addressed in a year or two. So let's give you an introduction to Magellan for Scalable Geospatial Analytics. This is going to be our main way into Spark. So the way we are going to do this is this Magellan has its own library. So if you look here, so it uses this Esri geometry library, which is attached to this Magellan Spark 1.5.2 cluster, because Magellan is not quite ready for 1.6 yet. And
I think the intention is to wait for 2.0.
Oh, okay. So
that's why it hasn't been yet.
Okay, that sounds good. So 2.0 will be screaming fast. So hopefully Magellan will scream with it. So, and I think the other thing we need is Magellan 1.5.2. So this is a snapshot jar. You built this? Or?
Yes, I think there's no official release yet.
Yeah, I didn't see it in Spark packages. So, you can go and search for it, or in Maven Central. So you built this from the GitHub?
Yeah, so this here's a bit branch from GitHub.
Okay.
Like an experimental 1.5.2 support.
Okay, so he made a jar, and then I just uploaded it, right? So basically, those are the two things we need, and we've attached them to this cluster. So then let's just get an idea now. So I'm going to sort of assign you as this homework. So this is basically the February 16th Spark Summit. It's 28 minutes or something. It's totally worthwhile looking at it, especially the latter part where Ram was talking about what will happen to Magellan in the near future. They're going to use much more interesting data structures and space filling curves and more fancier algorithms to speed up joins, because a lot of these problems come down to joins first. Okay, so, and these are the resources. So Ram's blog and Hortonworks. This is actually from the Amsterdam Spark Summit in 2015 talk. And this is the Zeppelin Hub view of it. So this is just a Zeppelin Notebook. Oh, by the way, Microsoft contacted me on Monday. They want to give 12 times more cloud computing credits than AWS for us. So that's a lot of cloud computing resources. And they are, is it all good? They're basically thinking of coming to visit us. So the Spark meetup, the week after the last week here, right? So this is second week of June. So I thought maybe we can, I can advertise it if they're definitely committing to a date, and we could, maybe other people are interested in it. So they have their own system called HD Insight, which is a different notebook-like layer that's running Databricks as well.
So what's their goal?
Well, I guess their goal is to not just have AWS be our engine. It's one goal, right? Which is nice, and it's they're giving us a lot of free cloud computing credits. I have been talking to Databricks to see if they can get, because Ion Stoica said at one point, and as it says in Wikipedia, that they will allow Google Compute Engine, AWS, as well as Microsoft as the underlying cloud layers, compute layers. So, but they haven't done that quite yet, so they're working on it. And if that happens, then it's just a matter of switching the stuff underneath, so it'll all be transparent, all the notes will carry over. If not, or actually in addition to that, I thought it might be worthwhile, especially if this course runs next year, to redo some of these things using their Zeppelin and Jupyter notebooks. So they're using open source notebook interfaces, not the Databricks ones. And that has some value because then you can sort of run the Zeppelin notebook locally and play with it. And then when you're happy with it, you can just use that on HD Insight. And also for the HD Insight part, they're not charging anything. So their business model is quite competitive. But of course, you know, I don't know, I'm not a businessman, but it's an interesting problem because if I can use Zeppelin Notebook and Jupyter Notebooks, then that actually increases value in a different way, right? Because students can, you know, they already know how to use these open source notebooks, so it'll be easier to plug and chug and do grading and things like this. So anyway, so what is the Magellan Spark project? Really, it's basically building on a huge library called the Esri, Environmental Systems Research Institute. And they're just making Esri's objects you know, more Spark friendly. And you have to watch the talk to get a more, you know, a slightly better idea of why it is quite subtle. Because you see, the fundamental problem is these objects that we're trying to represent shapes in geometries have to go through the Ethernet cable or whatever, right, between machines. So that process is deserialization and serialization, right? So that process basically has to be done very cleverly because these data structures are not just, you know, simple things like ints and so on. They may be tree-based and, you know, they're much more rich spatial data structures. So when you just pass it through the Ethernet cables, you don't want to lose the geometry. So you have to do things more cleverly. I actually don't know the details of what Ram and these guys are doing cleverly, but that's the main punchline. So you want to use Magellan. Okay, so the question is, do we need one more geospatial analytics library? You're welcome to watch this 4-minute spiel on it. But what I just told you is one of the key features. The other main points are here. This is Ram's slide 4 of this 2016 talk from SlideShare. And what he's basically saying is spatial analytics at scale is challenging, yeah, because we want simplicity and scalability. This is usually hard, but it's not because of Spark. Right? Then you have all these ancient data formats that are legacy formats that are not going to go away. So these are shapefile formats that have their own esoteric encodings of metadata and things like this. So we want to seamlessly handle all of that. That's another reason for Magellan. And of course, geospatial analytics is not very, very simple classical or old school business intelligence anymore. You really want statistical and machine learning to be operating in, nicely with your SQL queries and things like this. So Spark again provides a very nice framework for it. Right? So a lot of things are happening quite fast. Both input streams are quite big, and so by using Spark SQL in Magellan, we automatically have the Catalyst doing the optimization and Tungsten for better memory performance and so on. So that's the main punchline for Magellan, right? So let's quickly look at nuts and bolts of Magellan, and then I'll sort of, maybe I'll try to finish by 5, with an hour and 10 minutes. Good for you? Okay, about an hour maybe. So here I'm just walking you through the help file in the readme.md basically of Magellan in GitHub. So first we're going to import some of the basic objects we need. So we want to import Magellan point, polygon, and polyline. These are just points and polygons and polylines. And then we have some coordinate system. We want NAT83, you'll see why. And then some other Spark Magellan connectors, like Magellan context and so on. Some other things with SQL functions we'll need. And we're going to use the Java SQL timestamp library and simple date format. Okay, so now the first object is a point. Okay, so point is just our usual thing. We just have a sequence of points here. Point is just an ordered pair because these are points in 2 dimensions, and we can have a bunch of points like this. So I've just parallelized a sequence of points, turned it into a data frame, calling the columns X and Y, and I've just selected X and Y as a point. Okay. So I'm just showing you this data frame now. And, oh, interesting. Oh, thought I embedded some video, it's gone. Oh, well. All right, I'll just be the video. So basically, polygon is going to be, it's going to come from an array of points, and we're going to march through the points counterclockwise, as it's the tradition in this field, okay? So we march through the points counterclockwise, and that's going to, when it comes back, it's the outer polygon. And then some polygons can also have holes in them. So that will be another polygon inside it. But then in the metadata structure, you let Spark or Magellan know that the index of the outer polygon and the index of where this inner polygon starts. Okay, and then all you have is just a sequence of points with starting indices of the inner and outer polygons. So that's what was in one of the videos I thought I embedded. So now. Oh, they did, yeah, they just updated the effect. So anyway, I didn't save either or put it in GitHub yet, so that's okay. So polygons here. I'm basically making a polygon record, and that's this case class we made. Okay, so I'm going to basically create a sequence of polygon records. This just says the array the index starts from 0, and the ring is my sequence of points. And I've just converted this to a data frame. So then I can just show this as usual. So that just gives me, not sure why. That just gives me my polygon as a wrapped array of points, the wrapped array where the index starts. Okay. So this is just it's just this square that's centered at the origin and sort of touches the ones, okay? It's a -1, 1 square. So that's what we have. Now predicates are the other basic things. So we want to be able to do Booleans like within. So we want to know, take my polygons and select the point within the polygon, right? And this just is going to return true, because this point 0.5, 0.5 is inside this polygon, right? Okay, so that's predicate within, and the other predicate that's very useful is intersects, right? So here I'm just taking the points and doing a join first, and then with the polygons, and then I'm asking it to show, right? So if I, okay, so I'm basically seeing my point, and then the polygon, and this is a pure join. And then once I've done the joining of the points with the polygons, then I can do a query like this, where point intersects polygon. Okay, so this will be all the points that intersect the polygon. Okay, so here in this case, all my points actually intersect the polygon, so it's because these are just the corners. So now I'm going to just add another point, -2, -2, that lies outside this -1, 1 square polygon, and that's what I added here. So I'm going to call this more points. We'll also convert it to a data frame, and now if I do more points dot join polygons, I'm basically going to see the new point I added, right? And then finally, I'm going to do more points on join polygons, same thing, where point intersects polygon. So now -2, 2 is not in the polygon. Okay, so these are very, very simple 2 predicates and 3 different types of shape literals. And that's enough to do quite a lot of things, actually. So you now can have Boolean expressions with these literals and these predicates. You can express quite complex statements in this language now. Okay, so this is the Uber data for the demo that's done by Ram. And I think, let me see, it's already been downloaded for you. So if you do this in a new shard, the instructions of how to download are here. You don't have to repeat it. And okay, so here is basically the trajectory data. This is how it looks like. So you have an ID of the Uber ride, the trip ID, and there's the timestamp, and then latitude and longitude. Right. So these are all trip ID 1. So that's the same trip. So there's I think 172 trips or something. I'm not sure. So then the other thing we need is the shape file. So we're basically gone to San Francisco's city website and downloaded the shape files that tell you what the boundaries of different neighborhoods are in San Francisco, right? Soma, that Ram talked about in the video, is called South of Market, right? It's a neighborhood. There are lots of neighborhoods, there are 20-some neighborhoods. So these are the shape files. So if you actually look at the shape files, there is actually a directory containing supporting files, interlinked separate files, and they all share some information in this legacy format. So you need to be able to read this naturally, and that's what Magellan does automatically for you. The other format that we saw was GeoJSONs. Okay, so homework, watch this video. This is the technical one. 2016 one is slightly less technical, more about what they're going to do for the future. Okay. So basically, we now make a Uber record. This I'm basically taking right out of the Zeppelin Hub view, Ram's notebook from this talk from 2015. Okay, so what I've done here is just made a Uber by taking the text file, all of the Uber trips, and then mapped each line in that file into all these components, so basically split by tab and trip ID, timestamp, point, and pulling them all out. And then I turn them to this case class Uber record we just made. And then I repartition into 100, so I do things slightly faster, and to data frame and cache. Okay, so that gives me my data frame. So once I have my data frame, I can just do a count. This will take, I think, maybe 130 seconds or something, I don't know. Okay, so there's over a million records. So now that's cached. Now I'm going to do the same with neighborhoods. See all the San Francisco neighborhoods. I'm reading from in the Magellan format from this directory in the distributed file system we loaded, and I'm selecting the polygons and the metadata columns out of this and caching it. That's what I'm calling neighborhoods data frame. So and then there are 37 neighborhoods in San Francisco. And I'm just printing the schema, and it just says I have a polygon, and then I have metadata, which is a map, and the map is just as this key value pair of strings. So if I just look at the first two neighborhoods, this basically gives me, I've got a polygon array, which is my first node, and then I think this, every time I run this, it'll be different. So this is the neighborhood key, and the value is Twin Peaks. And the second one is a neighborhood. That's a different one. Pacific Heights. Okay. So I've just sort of done an explode of the metadata, and I've just seen this key value pair, and I'm seeing that a lot of the neighborhoods are there. Okay. So now the next thing we're going to do is trying to do a join. So we're going to basically join the Uber data where the point is within the polygon in the neighborhood. And then we're going to select the trip ID, timestamp, and then explode it by the key value pairs, the neighborhood and the neighborhood name. And then we're just going to rename the columns and drop K and show. So this thing will actually produce nothing, okay, when it completes in a few seconds. And what is going on here is a clash of geospatial formats, basically. Right? So Ram kind of goes into this in more detail in this talk. And what we are trying to do here is, define a transformer. This transformer basically will change the points into the right coordinate system that the shape files are in, right? So, and then this you can do really quickly in Magellan. So if you want to go between formats, and because of Scala, it's pretty robust. Right? So this is the transformer. The transformer basically is actually mapping a point to this function that returns a Magellan point. Okay, and what's going on inside is this NAD83 format that has the argument map zone 403. I don't know the details of exactly how NAD83 works, but you need to give it the zone ID, and then it will do your transformation nicely now. So it's all these. Do you know, Dominic, the NAD83 format? Okay, it's in Wikipedia. You guys can figure it out. This is just right out of stock. Okay, so I've just defined this. Now, once I've defined the transformer, now I can just say Uber transformed is Uber.with columns NAD83, and then I'm just going to take the column point and apply the transformer by the function transformer. And this just adds a new column. That's what we have here. And finally, I can now, in the appropriate coordinate system, I can do this. I'm doing the same join and asking which points are in which neighborhoods. So now joined, just showing the 5 of them. So this trip ID is in that neighborhood and so on. Okay. So, and then if I count, this is would be about 130 seconds. I'm going to find all the trips, all the rows in the trips that actually fell into one of these 37 neighborhoods, basically. Right? And that number is, so there are some rows in the Uber data, 43,651, that are not in the neighborhood maps. Are these the ones that go into the airport or something?
Yeah, something like that.
Some Uber trips, so they're not in one of these neighborhoods, right? Okay, so finally we have, we can basically find how many trips are in each neighborhood, because all we are doing is group by neighborhood, and then we are aggregating the count distinct trip IDs, and then finally we can order by a descending of the column trips, because we've aggregated it and named that column as trips, and so this will show you the most popular neighborhoods, basically. Right, so that's 43,651. So then we are able to find out how many trip IDs intersect with each of the neighborhoods arranged by. So south of Market is one of the most popular neighborhoods. Okay, so I hope 1 hour is enough for you. So this is just motivation for Dylan's bit. What we're trying to sort of point out here is that we can have these shapes, geometric shapes that are two-dimensional, and then we can have time IDs, and then by just combining the shapes with time intervals and using predicates like it belongs to and intersection, we can express quite a lot of spatiotemporal queries in this language. And that's basically where we want to go with it. And I think in the end of Ram's 2016 Spark Summit East talk, he goes through some of these ideas of making this faster, because currently I think it's mainly doing broadcast hash joins. So if you have one table which is small, like the San Francisco neighborhood table is only 37, and then the other thing is like 1 million, so you're just basically joining them up. So then the Catalyst engine will automatically figure out that the optimal thing to do is to broadcast the small table to all the nodes and then do this sort of hash join. If they're both big, then it'll do a Cartesian join, which will kill you. So what they're trying to do now is to use more clever spatial indexing strategies. Like, Z-order curves are basically one-dimensional indexing of space, right? So you have one-dimensional indexing that will sort of weave through space so that you can exploit that indexing to do some pre-computations so that you are more clever about how to join things. So you don't join things you don't want to join, for example. So that's all work in progress. Okay, so let me just pass it on to Dylan now. So Dylan's our first project speaker. Okay.
Yeah, so essentially like the motivation between this is to work with trajectory data as we define here. So it's essentially the sets of time space or points in time and space. So they have an X and a Y and a timestamp for each point. So it's like the Uber data we had before. And so the data set for this is Microsoft's research. They've I don't know if they collected it or they partnered with some people in Beijing, but it's a massive data set of taxi trips. And as part of that, their research have released a little sample of that. So it's not the full data set, but I think it's around, like 18 million points. And so that's what we're going to work with here. So it's slightly larger than the Uber data, and it's more real world data. So for that Uber data, they've taken it and sanitized it to preserve to make sure the trips are anonymous. So taking points off the end. So so this is a bit nicer. And just as to explain some more things, I'm just going to go into detail on how to download the data and that sort of thing, because the way we do it here is slightly different from anything else I've come across. So if you see on the page here, these are the actual downloads you get. So it's a whole bunch of zip files, and each of them contains a segment of the data. So I think there's 14 all up. And so it's a bit tricky to download instead of, because the past downloads have been one CSV file, we just download it, load it into DBFS, and you're good to go. But thankfully, people have written an interface to Hadoop, so you can just directly read zip files without uncompressing them and just read them into Spark. So this link goes into detail on how to do it. So I don't really want to cover it here, but it's just one of the Databricks help guides. And so you just have to take a library and attach it to your cluster. So it's Hadoop zip format, and it has all the functions in there. But essentially, it's an interface to read these zip files nicely. And you could write a shell script, unzip all of them, load them load them that way, and you're good to go. But this is a lot easier. So I'll skim over this because there's not a lot of time, but essentially it's just, instead of using shell scripts to download everything, we're just using Scala libraries to get access stuff and download things. So, and this goes into detail on essentially like what I'm doing here, except I'm downloading multiple zip files instead of just one. So we have the data now, and we've loaded into DBFS. So it's just a whole bunch of zip files in a folder, and it's not really useful at the moment, but it's fairly easy to just create an RDD from these. So in this step, we're just loading it from DBFS. This is essentially saying it's a zip file, and I can't remember exactly, but so it's essentially we're making an RDD, key value RDD, where the key is the file path or the name of the name of the zip file here, and then the contents of value is just the text that's contained in that zip file. So these are the zip file. These are all the trips. Oh, sorry. This is each taxi ID. So each taxi in the data set is given an individual ID, and slightly different from Uber in that though it just contains a whole lot of records for that specific taxi. But the Uber trips, they're split into individual trips. So if you wanted to do anything interesting with this, you'd actually have to go through and figure out a way to split them into, sessionize them into individual trips.
So Dylan, those are the names of the files that you unzip?
Yes.
Files?
Yeah. And this is essentially, this is what they contain. So it's just the ID, a timestamp of when the record was taken, and then the coordinates, that thing, and it just one. So each taxi has a file like this, and I think it's it.
Is this something like geotagging or something?
I think they just have GPS readers in the taxis, and so the files themselves, they're not really geotagged. It's just logs from the GPS of the taxi. And I think and just whatever they're doing, it's every 5 seconds, they just ping the GPS and record it. So yeah, I think they know. And so what we have to do, they don't give you any additional metadata, so you'd want to extract that yourself and do that fusion yourself, because the data set just doesn't have it. So that's partly the motivation of what I'm doing now. I don't quite get all the way there, but it's laying out the framework to do so. And so just to continue, we're taking these key value RDDs, and I want to work with lines, so we just, each entry in the RDD is one of these. We split it, add it, and then turn it into a data frame. So it's essentially just one big column with all the lines. So just, yeah. Oh, sorry, yeah, and then now we want to actually, we want to do what we did with Uber data and pass these lines and turn them into or define case classes to read it into a data frame, so we can get nice columns for it. And these are essentially just the same imports as we had with Magellan, some additional stuff just for the timestamps. And I think I just copy pasted this and replaced Uber with taxi, but it's essentially the same thing. So it's the ID, the timestamp, and the point. That's a Magellan point, but essentially a Magellan point is just a wrapper for two doubles with latitude and longitude. So they're wrappers for Esri points, which are wrappers for lat-long points. And yeah, so here we are actually doing the bulk of the parsing. So if you scroll up here, you see the format of this is ID, timestamp, latitude, longitude, and so it's a CSV file. So just split on the comma, and then to convert these to the strings to ints. And if you look at this date format here, this is just part of the Java date time library, and so you define the format of the date in there, and it just gives you a nice long, it gives you a long, and that defines the time in seconds, and it has some helper libraries around that if you want to pre-print it or work out time intervals and that sort of thing, which is what we'll get into a bit later on. We create the points. Yeah, so these are the Magellan points, and then just return the record of the case class we defined above. And this here it's because we're dealing with nice messy data, so we just want to. So if anything here fails, so it could be something like, you could have errors where there's just 2 commas. The field's missing, that sort of thing. So currently, if you're not handling the errors, it just crashes and you have to start again. So if we're just catching any possible errors and creating bogus points here, and we just filter them out here, and that saves us. So it may be worthwhile if you want to work more with this data set in particular, you'd want to look into it and see what the errors are, if it's something you can correct, or if it's completely garbage. And there's a chapter in what's the name of that Spark book? The
Advanced Analytics in Spark.
Yeah, that book that goes into a bit more detail. So that's working with a different data set, but it goes into things like, well, what do you do with messy data, noisy data? What cases you'd like to handle? Which cases are just you're better off ignoring? And I think there's no link there currently, but I can put up a link so you can have a look at it later on. And so after all this is the data frame we get. So this is just that CSV file, but a data frame. And just an additional step, because this Magellan's still stuck on 1.5.2, if you wanted to look at any of the new features we've looked at, so like the data sets and whatever additions we have in newer versions of Spark, you can't actually use this. So you can take this and save it as a Parquet file in DBFS, and that you can access that from anything that can read a Parquet file. So you can have another Magellan cluster, read it from there, and work with it like any other data frame. Just bearing in mind that you have to strip out these points here and just work with longs, where you could convert them to Esri points, something like that. But also, essentially, it's not a supported data type with Parquet, so you just store the doubles and you work with it that way. And yeah, go a bit more into that and like where we use that in the next notebook from here. But so yeah, we've processed all the data and it's in a nice data frame. It's easy to work with. So it's what's 17 million, almost 18 million records. And so we're starting to work with this. So like Raz said earlier, Magellan builds on top of Esri, and it exposes like a nice SQL interfaces to some of the functions, but most of them aren't covered. So actually, we're just directly importing them here. Because it's essentially we want this function here. So it's the geodesic distance on WGS 84. So it's a distance from the distance of between 2 points on a reference spheroid that's used quite commonly in map projections. So it's the geodesic distance instead of just straight line. You get Euclidean distance, which is slightly more accurate. And there are other approximations you can use, but in this case, we use the Esri function. And yeah, there's another bit of Scala magic. So an implicit function, you don't have to call it. It's implicit. So if you're calling the function so this essentially converts a Magellan point to an Esri point. So we can feed Magellan points into Esri functions without having to create a new Esri point every time, or at least manually. So it's this, ignore this if you're working in Python or anything like this, but it's quite nice. And so now we're starting to get onto the actual constraint satisfaction bit of it. And so just to illustrate I'll talk about it a bit more. So the problem in general is we have a region of space. So for Magellan, if you think in terms of Magellan, that'd be a polygon of some sort. Or here we define our own class for just a circle. So it's your region in space. So the circle is just represented by a point, a center, and then a radius in meters. And then the queries we're thinking of, it's geospatial constraints. So it's objects intersecting a space within a given time frame. So we want to keep this fairly generic. So we define this trait here, and a trait in Scala is essentially just an interface, like a generic, or it's an interface, and you can define objects and classes that satisfy the interface, and you can call it generically. So we have containers of the circle we defined above, as well as Magellan polygons, but essentially it just defines an interface to do constraint queries in the way we talked about them. So we have a function here that just takes a trajectory data frame like the one we have above the taxi trips, and you pass in your start and end times, and you end up with a data frame that contains all the points that intersect that region. This is just a helper function for that. And so I'll just focus on the polygon containers because it's a bit more future-proof. It's working with Magellan types instead of our own user-defined types, which, it could break, that sort of thing. But as long as Magellan remains fairly stable on this part, it should work fine. So it's just to go into here, we essentially first we want to find all the points that intersect our region and time. So it's just the query. It's here is the timestamp of the point or after our start time, but before our end time. And that's a fairly quick query. You're not getting into any complex geospatial data types, but so it's a good first step to take. But ideally, that'd be something that also optimized by Catalyst, so that, you rearrange the order of the queries to make them more efficient. But so I like reasoning about it this way because it feels more efficient, even if it isn't. And then yes, so now we have the polygons intersecting the time region, and then we want to essentially just join them for original trips. So we're passing the polygon data frames here. So it's essentially like the polygon records we had in the earlier talk. So it's just think of it as a sequence of polygons, and we want to find points that pass through all of them, or trips that do. Unfortunately, I noticed an error not long ago that so slightly adjust what it is, but it'll give you points that pass through at least one of them, and hopefully, if whatever bug it was gets fixed, it'll work fine. But so this just returns all the polygons, all the points that go through all the polygons in that region in time. And I don't know how much sense that made, but there's an example here just to hopefully make things a bit clearer. So we have our polygon record like in the talk. We define it here, and the reason it's in this, or you'd redefine it, is there's occasionally been a few bugs in Databricks where case classes defined outside of cells aren't registered. I think there are ways to get around it now, but I just didn't have the time to look it up. So yeah, this is a polygon record containing these points, and this is a little polygon, and it just represents a sort of vaguely rectangular area around Tiananmen Square. So this is just me going on Google Maps, dropping pins and getting the locations. And then now we're creating a polygon container here. And we're just, so it's an array, or it's a sequence of these polygon records. So although it's only one polygon here, you can essentially have as many as you want. You can keep going. So so long as you're not too crazy with it, it'll parallelize fine. So long as you're not creating a massive sequence of them, it's fine. And then to continue with the example, this is the times we're interested in. So these are just I think the ISO date. So February the 3rd, and it's about 5 minutes, and that's the time frame I'm interested in. And then because we've got these nice generic functions to get the trips we need, we just call that function, and we end up with a list of these trips here. And then the next step from that would be just to extract the IDs, and if you extract the IDs, you can start working with just the trips themselves. You can find all the trips that intersect these regions, and then you pull out endpoints. And so you can answer, if you want an application for this, it'd be things like, finding popular drop-off locations, like in the Uber talk. So, or I don't know, you could use it to target advertising. If everyone that goes to Tiananmen Square goes to a certain place, you have some targeted advertising and do whatever. But I didn't go into that, but that's what you want to do with it. Or
everybody wants to sell something.
Yeah, and then there's also like defense applications or whatever you can think of. You can have a license plate reader, and that could be your source of trajectory data, and you can find out potential endpoints of speeders, or someone's stolen a car. You can find out what car it likely is, that sort of thing. But in order to do so, you want a nice set of trajectory data you're actually interested in, and you want to have questions there to ask. But next, so I don't want to spend too much time on this, but if there's any questions, let me know. If there's anything you want me to clarify, but next I'll go on to the map matching segment.
I have a quick question.
Yeah.
So suppose somebody goes and grabs all the earthquake data, right?
Yeah.
And so now I can basically think of these as points that we have to launch with a timestamp.
Yeah.
And that's about it, basically. Oh, and then there'll be other columns like magnitude and all sorts of things.
Yeah.
So suppose I'm interested in like finding all the earthquakes that happened in some radius around certain key fault lines, for example.
Yeah.
Then I could use your circle operator. And if I ignore the depth, then I can map it to two-dimensional coordinates and then use your circle literal to essentially do intersection queries generating data.
Yeah. So you can say they do that sort of thing, or you could also use it to define like boundaries around regions of interest. So if you have, if you want to find people that travel past certain shops during the day, if you just work with the polygonal definition of the actual boundary of the shop, you're going to miss out on data because people walk into the store. The GPS data is quite noisy, if they even get a signal at all. So you want to use this to fuzz the results, so you can sort of work with all these correct for lossy and noisy data. Sort of talking about and with that you also want to get into map matching of some kind. So what is it? It's taking noisy GPS trajectories. So I think this is someone driving it down the highway, and just due to geography, weak poor signals, that sort of thing, the points will tend to jump around if they even correspond to a road at all. And there's things like that, and there's also just that the maps may be wrong, like the images that you're looking at that don't quite correspond to where the roads really are. So to be able to work with that more, you want to essentially snap GPS points to their closest roads or footpaths or whatever, depending on the mode of transport or suspected mode of transport. And so that's what we do here. And so what we're using for map matching is this thing called Grasshopper. So it's Grasshopper, the company itself. It's essentially an open source Google Maps style service. So you go on there, and it provides routing and develop APIs. But as part of this, they've got a fairly extensive open source component. So a lot of their backend they've released online. They've released on GitHub. So it's what we've built on here. So they've got traffic simulation, urban planning, path routing, that sort of thing. And they've got released a map matching library that builds on the core Grasshopper libraries to do that snapping we talked about. And just brief aside, there's other things that work with built on top of Spark that do this kind of. So this is BMW has released what they use for this, what their research departments use for online routing and map matching in cars. So it's both streaming and sort of offline data analysis. But haven't used this here just because it requires like a Postgres database to be set up, and it runs inside Docker containers, which you could do through Databricks, but it's not fun. So so Grasshopper, the map matching is just a Java library. It's not Spark aware at all. So there's some things we have to talk about and consider and work around to make it work properly here. So there's a few libraries we have to attach. So there's the Grasshopper library itself here. So this is just an Israel like import library or create library, and you just give it the Maven coordinates. We use Magellan itself here, and we also use the same spray JSON. That's just a JavaScript decoder and encoder that you see why we use it a little bit later on. But yeah, so Grasshopper, the way the API works is you have a global Grasshopper object, and you feed it like a sequence of points. So, and then it gives you likely matched trajectories. So it's nice like that. But one thing to keep in mind is the documentation is not great. So if there's anything you want to do that isn't in examples they give, you're going to have to do through their code, which thankfully seems to be getting better and more commented as time goes by, but it's still not great. So there's a few things to do. So just to start off with, we have to, you feed it in OpenStreetMap data. So if you feed it OpenStreetMap, it's a community crowdsourced, community crowdsourced geospatial, also maps essentially. So most of the world is covered in places, parts of Europe especially. I feel it's even better than Google Maps. But if you just think of it as Google Maps, but you can download all the map files they use. And so this is the downloading of the data itself. So we download this from a place called Maps then, and then they just have city size extracts of OpenStreetMap data. And that's what we use here. So this is San Francisco. And you put this into DBFS, and then...
That's the whole city, isn't it?
Yeah. Oh, it's I think it's slightly larger than the actual city, just because we've got trips that aren't technically in San Francisco, so they go out to Oakland, to the airport there, but it's about it's a decent sized bounding box around us. It's a sort of greater metropolitan area. And because, like I said, Grasshopper isn't actually Spark aware, we have to get kind of sidestep it. And because it relies on one global map matching object, so like this hopper here, to get around it by pre-processing the data. So Grasshopper takes your OpenStreetMap and creates its own internal graph representation, and then you can store that on disk, and then so it caches it, so it doesn't have to recreate that graph every single time. So if we we initialize it once on the just locally, so we're not distributing it to any machines. We create this object, store the files on DBFS. Then we can get around it by creating a new matching object for each partition locally, so they can access all the files there, and you can essentially treat that object as local to that partition. So you're not having to serialize and deserialize this Grasshopper object. So this is sort of a workaround for that, and so that's how to get around that. But I'll keep going a bit more. So this is essentially our table here is that data set from Uber that we used in the initial Magellan thing. So we've created a shared table here. So it's one of the tables here in Databricks. So it's not actually using a Parquet file, but I just ran out of time to get the Beijing data to work here. But so it's the Uber table. If we go in here and look, it's sequence of, it's trip IDs, timestamps, time. So this is the time, and I think it's just in seconds from, I'm guessing, the Unix epoch. And then this is the coordinates of it at that point. So and this is how we get around not being able to use Magellan points. And here we're just, so for the map matching, especially with the things we're doing, it doesn't make a lot of sense to work with trips that don't only contain 1 point. So this would be a result of either noisy data, or someone they've accidentally recorded a trip and it's false, or it's because they've cut off certain beginning and end points to preserve people's privacy. So we just throw these data points out, and in fact, Grasshopper will crash if you feed it in less than 2 points, because it doesn't really make sense to map match the single point, because there's too many likely things you could fit it to. So, and especially around intersections, it will be almost practically useless. So we filtered these out, and now we're just making a set of tuples. And so we're taking our data frames here, and we've made this big RDD of, so the integer here, so that's the ID of the trip itself, latitude, longitude, timestamp tuple. So essentially you have a key value RDD where the key is the taxi itself or the trip itself, and then there's an array of all the points, time, space. And this is essentially, and the reason we do it like this is because that's closer to the format that Grasshopper wants it in. So you feed it a list of latitude, longitude, timestamps, and that's what a map matches on. So it map matches on the entire sequence. So there's certain heuristics it can do around that to sort of adjust to, there may be patches of outlying points that just don't make any sense. So we can feed the whole sequence. It can sort of correct for those a bit more. And this is a messy Scala just to get around the way that the map matching works. So Grasshopper, it assumes that you have a GPX file. So it's quite common in GPS readers, like commercial GPS and handheld GPS things, and that's the format they give you. So it's a big XML file of latitude, longitude, time points. And we're just essentially creating a GPX file in memory and feeding it to Grasshopper. That's what it does here. So I'm not going to explain it because it's running out of time. And then just to go into some actual more detail about how Grasshopper works. So this is the low-level API. No, sorry, I thought I had the right link here, but essentially the way that Grasshopper works and what makes it fast and useful is it creates that graph that we talked about above, and then it defines a contraction hierarchy on it. So it's a way to collapse nodes on the graphs into shorter, more efficient points. So you're not working full graphs. So it speeds up queries when you have those options enabled. There we go. Yeah, so this is the more in-depth layout of it and how it works. And so they've published several. I think they've published a few papers relating to this. So I think it's some people's thesis work, and then they went started Grasshopper. But if you look into this for more information. And actually, recently it's not currently enabled, but there's a fork, or there's a improved build of Grasshopper that actually uses hidden Markov models that should actually speed up all these queries quite a bit, but it's not implemented yet, so it's not. Don't have it working here, but it's sort of very breakneck pace. I think the last updates to the libraries were within a few hours. I think when I last checked. So this in a few months this will be completely need to be changed,
But all their data structures with these contraction hierarchies and fancy multidimensional data structures, they are staying in the RAM of each node, is that right?
Yeah.
So you kind of take advantage of that.
Yeah.
And still play with this Spark framework.
yeah, so that's how we get around. Yeah, so essentially it is always in RAM, but it's before we got it and worked around it, it was in RAM on the master, so it wasn't actually getting shared between the nodes, and then it crashes because it's not a serializable object. So, and even if it was serializable, you'd be sending a large data structure through the wire, and that would just kill any performance you have. So even if this did work serialized, it wouldn't really be worth it to do it that way. And that's sort of just the way it was written. It was, it's a single machine Java library, so it's, it doesn't take anything into consideration. So you'd be better off working with something like the BFIT above there if you're doing sort of large scale commercial things on Spark. And that's sort of utilizing database, like modern database technology to do some things. Yes, so essentially, and part of the reason why the stuff I'm doing here is fairly basic. Up until recently, most sort of geospatial databases and libraries, they've all been focused around single machine things. So, you want a beefy server so you can process the entire world map from OpenStreetMap. And there's not really been much thought or work put towards scaling this up until things like Spark came along and it became sort of cheap and it became the cheap way to do things. So the tooling is really starting to speed up now, and there's multiple competing libraries to do similar things in Spark. And this is just filling in some of the gaps that they don't quite fulfill yet. And so, to get onto actual map matching, this is a function that returns Grasshopper, so it reads it from that. This is the location we stored it in DBFS, and you just have this allow write, so it just has read-only access to DBFS, because it creates a lock file when it's running single-threaded, just so you don't write over it in a parallel thread. But if you set it to read only, then it ignores this lock file and just reads it from memory. And this is the bulk of the map matching. It's one function here, and a lot of this is just to work with the GPX files. So I'll skim over this because there's not a whole lot of time. But so we have the map partitions. This is like a map on an RDD, but instead it maps each partition, and then for each partition you get a sequence that corresponds to what you have in the RDD. So in this case, it's the ID, and then latitude, longitude array, like tuples we defined above, and then depending on how Spark decides to partition it, you'll have it that way. But because of the way we've defined it, each trip is going to be completely defined in one partition, so you're not going to have multiple taxis in different partitions, or the same taxi in different partitions, where you wouldn't have the complete information on one partition, which means you can't look around this. So so I'm just going to skim through this, but essentially we set some options here in Grasshopper, do the map matching. These you have to tweak a bit, because if it doesn't find any matches, it'll crash out, and you have to set a tweak in to find it. So it needs some fine tuning to actually work properly. And now we've got map match trips, and these are just counts of these are how many data points we have in the match trips. So it's the ID and the number of data points. And some of them you'll find that after map matching, some of them will only have three data points. If you want to explore that, that's sort of what I did before, but now just to show it up a bit better, we want to have some sort of visualization of the actual trajectories and see how they map match. So this is where we bring in that spray JSON. So this cell here essentially defines a way to convert this table, the table of points or latitude longitude points into JSON, and then we feed it into this JavaScript library called Leaflet, which is just an open source map viewing application. You can feed it in GeoJSON, which I mentioned briefly before, and then you can visualize that. So skim over this. And so this is just one of the trips of map matched, and I just picked this one because it was one of the longer trips. So this is a trip in San Francisco. So starts some on the freeway here. You see in purple, you have the matched trips. Oh, sorry, kind of yellow, orange. That's the broad GPS points. And you see that the parts that they're in the ocean. So this is why you want a map match. And this is the route that graph chooses to match it to. You can see it's not fantastic because you're not sure if it's actually matched. Yeah, so this is where you want to tweak those parameters above and just make it work properly. But there'll just be some cases where there'll just be certain trajectories that just won't match correctly. But with updates I mentioned before, there should be like a significant improvement in the accuracy and speed of these map matching.
You can take into account the importance of the road. I think that's what GPS navigators do.
Yeah.
They prefer the likely road first of all until they detect significant distance from the main road. And
that's something that would be quite good to get into if you have the appropriate data set for it. So so it's something we're quite interested in. I was quite interested in working on, but you need a lot of traffic data and historical traffic data to start weighting the roads.
But I think the hidden Markov model will really help with that.
Yeah.
Because that will essentially treat probably these edges as hidden states you easily need them.
And also, another thing to look into is also if you were to do that, you can, I think I just found a couple of days ago, you can download every single publicly uploaded GPX file that's been uploaded to OpenStreetMap.
Cool.
So that's a lot of data. I think it's something around 400 gigabytes uncompressed of the entire world, and it's lots and lots of GPS points. So you can start using that to build up start weighting that road graph that you create to frequency of travel. But and even with that, there's certain things you want to take into account. But that's if you wanted to make this better and more robust, say in like a commercial setting or a commercial device, you'd want to take these things into account. And so this is basically to the start here, reading OpenStreetMap data, and don't have a lot of time, but just
15 minutes.
Okay, so this is, I think, the part that I enjoyed most out of this. So this is it's essentially starting to do what Grasshopper does, but we're using graphics for it. So it's taking the OpenStreetMap data, bringing it into graphics in a way that you can run queries on it. So essentially we're building up a road graph in graphics. And I currently don't do a lot with it because a lot of it's just time's been spent passing the OpenStreetMap data properly, getting it to cleaning it all up and that sort of thing. And so if you notice any inconsistencies, it's because this is recently been rewritten to work with the dataset API, which has made things a lot cleaner than it was. Yes, and before this, there was a bit crafty Python script that passed all the OpenStreetMap files and worked that way. But now this is using Osmosis, which is I think it's the official implementation of the reader for OpenStreetMap data. So OpenStreetMap data is most of the time it's distributed, or one of the main formats is a protocol buffer file, and that's just an efficient binary representation of the maps and the tags and the associated nodes. And it's a lot faster to pass than the older formats they have, but this requires a bit more work to work properly. So that Java API just defines methods and interfaces to reading and processing that data. So to start off with, I haven't really covered it in much detail, but the main data types, or the way OpenStreetMap defines its data, is in terms of nodes. So nodes are just points. They're not necessarily, so they're points at some location, and they're used to define a lot of things. So roads, they're sequences of points, and the sequences are defined by way. And so that you just think of them as like polygonal lines, and it defines it. And then you have even points of interest that just been like water fountains. They're marked with a node. So we have this OpenStreetMap file that has an extract of Beijing, and we want to extract all the roads from that to create our graph. So we want to do what Graph is doing. So these are a set of the tags that or that OpenStreetMap uses to find something you can drive or travel on. So it's motorways, motorway links, roads, and then there's a few other ones that I might take out. But so you can't just query for all the roads, because people like to tag them as different things, and because it's all crowdsourced, it makes the quality of some of this not questionable, but it just, there's not necessarily always the best consistency with all the data they have, so it makes some of this a bit messy. And then, so we've got this protobuf file here, and this is a osmosis reader. So that's just it outputs a sequence, or it runs on a sequence of entities, and it's in OpenStreetMap entities. And with that, you can sort of, I don't know, while it's going through that stream of entities, you process them into whatever you have. So at the moment, we're just collecting all the nodes. Here we have nodes that we just keep appending to, as well as a list of ways here. And this here is just filtering out all the ways that don't have tags in that list we defined above here. And then we run it, and then it sort of populates those arrays we defined here. So this is the data set containing this. So it's just ID, latitude, longitude, and then tags, and that gives you this data set here. And the reason we use a data set instead of a data frame is just because a lot of the things we're doing are quite iterative. And especially in Spark 2.0, the data set and data frame APIs are going to be unified. So a data set frame is a data set, but it just has, essentially with a data set, you're defining the rows yourself, or vice versa. And so these are just all the raw nodes here. So these are the tags here. So I'm guessing this is just this will be the node that represents the center of the city. And this, all the tags here are just different names and different Unicode errors. And this will be all the different languages that they support. And go through here, and there's traffic signals. And if you see these untagged nodes here, those tend to be nodes that are associated with roads or ways, so they don't necessarily have any tags. But you're looking to, once you get into.
So are there any Mandarin? Is that the bus stop thing? Is that really bus stop? Or?
It's probably the most of some bridge, probably some transport big user.
Oh, you know that one.
But yeah, so this is essentially every single node that in that city extract. So it's more data than we need for the graph, but we'll get to filtering that out a bit later on. And then we also we want to process all the way data. So a way is essentially just has a unique ID, as well as some tags which are various things, and then there's a sequence of nodes that defines the way. So then you have like roads here. This is the ID of that way. There's the tags there, and this is the node IDs of the nodes that belong to that way. So these are just, I think they're defined as 64-bit integers, and that's sort of unique to OpenStreetMap. And if anyone does want to work with this, bear in mind that it's unique to that version of the OpenStreetMap extract, but if there's it's not necessarily constant. So if you take extracts from OpenStreetMap that's slightly out of sync time-wise, there's a chance that things have changed around, so the IDs might change.
These are your PDF files?
Yeah, so it's essentially OpenStreetMap will release, I think it'll be like 10 minutes, they release an updated version of the Planet OpenStreetMap file that's with all the edits. And then the people doing extracts will take periodic snippets from those. And there's warnings that you just bear in mind that the IDs aren't globally or over time unique. They may change as things. So it'd be if for certain things, like say if a road needs to be subdivided even more. So if like the polygonal line isn't high enough quality, it might be subdivided into new points, and some of those in the way might change. So, and corresponding by IDs might change as well. So
for the entire file globally.
Yeah, I'm not sure. I'm not too sure exactly how that, if it actually does happen, but you don't rely on them being the same. And then so we have all this data here, and for what a lot of what you want to do, having a graph of every single node in a road, that's more information than you actually want to deal with. So what we've worked on here is to actually, once you have this graph, you want to just think of it in terms of intersections instead of as points. So that, but with the option to sort of go between those representations as you want. But I say it like we thought this ahead, but it was really just because it crashed when you're running certain algorithms with a bit larger graph. Just because it's graphics in many ways is still quite experimental. But so this was essentially here. We're just we want to start identifying any potential intersections, and the way we've done it here is just to take any nodes that occur more than once in the ways. So it's if a node occurs in multiple ways, then it's most likely where those two ways meet, and that's how we identified them here. So this is just what we get from this counting. So this is a group by node and count, and then a filter to remove any nodes that have less than 2 points. So the section, and then we'd map it just to extract the IDs. So this is just a data set of node IDs like this. So this is what you work with, and this is sort of the step here that sort of could potentially this will break if you work with larger extracts. So that's something that will need to be changed, but we'll take this RDD here, collect it, turn it into a set, and then broadcast it to every worker in the cluster. So it's fine because it's a big list, but it's not the bottleneck in this situation. But if you're working with something the size of the planet, where this list here could be millions and millions of nodes long, that's where you want to think about distributing a bit more. So this is what the set looks like. Not that it really means much here. And this is a reflection. So this is what the nodes look like. And in this one in here, we're just getting all the distinct nodes, just making sure they don't repeat here at all. So this is the data frame or data set of all the nodes in the entire Beijing area. And then now we just want to start extracting the ones that we are interested in. So these are the nodes that correspond to points in a way. So we're just filtering out all this irrelevant node information. And so we're just doing a join, and this is the data set join with. So we're joining the node data frame, the data set we defined above, with the data set of the node IDs and the ways, which is what we defined here. I think, yeah. So these are the nodes that occur in a way, in the ways we are interested in. And so we're doing a join with those two data sets. And this is just so we can extract all these tags and meta information. And the way nodes data set here contains the metadata and location of all the way nodes we're interested in. So that's essentially what you need to start building up a graph. If you think of these as, this is a vertex in a graph, these are the attributes, and that's essentially what you need to do to define a vertex in a graphics graph.
So that's now a vertex, so the intersection node is a vertex in this new coarsening graph you're defining, right?
Oh, so this is pre-coarsening. So this is, yes, and we'll get into coarsening here. Yeah, so this is where it gets to be a bit slightly messier, and this is where we're taking all the ways, taking all the nodes in those ways, and identifying which nodes are intersections, or taking that set we have of that broadcast variable we had that had all the intersection sets. So the intersection set here, and then we're tagging each node in the data set with a Boolean to say if it's an intersection or not. So we get this. So this is the way ID here, and then it's the node IDs. There's a sequence here, and it says true false to say if it's an intersection or not. So this is sort of when we start coarsening. This is just a little visualization. So this is the distribution of intersections. So you see most of them aren't there. So that most ways only have one or two intersections. So it means if for a lot of ways, you just collapse those down to one or 2 points, which can lead to a lot of space saving. And now, this is where we start to segment and sort of coarsen our graph. So we take an array here of node IDs and intersection booleans. And I had this all nicely wrapped in classes, so it made a bit more sense to read, but this wasn't working properly with the dataset API. I think it might just be because the dataset API is still a bit experimental, so it's not the nicest to deal with. And yeah, I was getting error messages twice the size of the page, so it's something with the code generation in New Vision Spark. But
about 2 minutes.
Okay, so yeah, we have these segmented ways here. So essentially, we just have here we start defining the coarser nodes. So it's just way ID thing, and these are the collapsed vertices here. So this is an intersection node that's collapsed multiple nodes into it. So it just maintains a list of contained nodes. And then we map it and we create, so this is essentially what will become our, it's essentially what become the edges in our graph. So we have these coarser nodes, they represent an edge in the graph. And then the vertices we defined above, or the data set we defined above, it just links to the nearest intersection node. And
so the sequence of nodes along the way that doesn't intersect with any other way will be identified with the closest intersection.
Yeah. And then each edge maintains the original way ID it belongs to, just to make things easier. If you would add tags and that sort of thing here. Yeah, so these are the edges you end up getting. So these are node IDs, and these are the attributes. So these are the way IDs that it belongs to. And then now we need to create a graph. So we create a graphics graph, and then that's what we have. So these are the edges we have. These are the vertices we have. And ignore this. If you see this is just with the way it's just Java implementation details. It's a name mangling, but these are actual values. They just don't work for the printing. And just really quickly, we have a graph there, and it's just intersections and nodes and it doesn't really have any information with it. But if you were to want to do like shortest path routing, I was going to say anything like that, you want to have distances associated with it. And essentially we bring in Esri to do that, and we just find, we take the nodes, compare the latitude and longitude, get the distance in the reference spheroid. So it's not necessarily quite accurate depending on terrain, that sort of thing, but it's a good enough approximation. We get distances, and so you end up with the edges. So this is source ID, destination, way ID, and then this is a distance between those two intersection points. And we take into account the fact that if they're collapsed and nodes into them, just because, so we take the distance between all those points along the line instead of just taking it between the two intersection points. And then I was going to hopefully try to test some of the new, well, it's not the new, but the graph algorithms and graphics in Spark 1.6, but ran into the same problem where I've encountered a lot of times. And if you run this, it crashes the cluster, so don't. But this hopefully will get fixed, or there'll be some workaround. But as of yet, I don't know, there are things that could be done to work around it, but not that have been done. And this is ideally something that will be fixed that graphics itself will fix, because it doesn't really give a lot of information as to why it crashes.
Something that Databricks are supporting, like the explicitly see.
Yeah.
But so also you could do this last bit in graph frames as well. Yeah,
so I didn't quite have time to do that, but but because essentially graph frames, they're built on top of graphics. So if it's a fundamental problem in the way graphics does it with larger graphs, it might just be something that needs to be, you need to work on the terms of graphics itself.
Hey, let's give Dylan a hand. If you have maybe one or two burning questions, you can ask him, and then those who want to run away can run away.
Yeah, and this will go into the course cluster with some more links, so just a bit more standalone, so I don't need me talking the whole time to understand what everything is.
So what's the hobby to write so long spreadsheets so you have some degree work?
No, I mean, I think mainly Dylan worked for, was an intern for Wynyard. And this is like a much sort of more generic robustification of a lot of that. And it's also aligned with the new versions of everything.
Yeah.
So it could be potentially,
Yeah, especially the graphics section, because when I worked on it, data sets were a thing. So this is like a lot simpler to read and follow along with than earlier versions.
Yeah, because it's type safe.
Yeah, and then and then before that, it was either working with data frames or RDDs, and so you don't get the benefit of a lot of type
There is
information.
one unfortunate thing with data sets. They don't push down predictions.
How do we know? I'll follow her. Yeah, but then it's at least, even if performance-wise it's not as good, well, hopefully it should be, but it's a lot nicer to deal with for like this type of thing down here than, let's say, working with data frames, just because you have the type information you provide, so it makes things a lot easier.
So here's the list of projects talks. If there's a number 1 next to you, that means you're speaking next week. So you're ready for next? Sorry? No, there isn't, because the week after next is like, so a lot of people ask this, so these 3 people are